So now net torque. From the figure here, the forces all exert corresponding torques. Like you see, we have forces being applied in all these different directions from the pedals on the bicycle wheel and the chain and so forth. So with the exception of the force on the axle right there, that would not be exerting a torque because there is no radius away from the pivot. So there's no moment arm, so no torque. With the exception of that one, the sum of the torques is how we would read that, would be equal to a net torque, kind of like a net force, right? And all we do is we add up all the torques, just like we were adding up all the forces with non-rotational forces, okay? Pretty straightforward. So just like you would expect, probably. Okay. I don't think I need to say much more than that. Okay, so then we have this. A capstan is a device used on old ships to raise the anchor. So basically, we have the anchor chain here for this tension force. Maybe it's a chain, maybe it was a rope, I don't know. Nowadays, probably would be a chain. So anyway, this guy here is on the end of a long lever, and he is applying a force as he spins around and winds up the chain. And then thus raising the anchor. So if the capstan turns at a constant speed, the net torque on it is 0. The rope tension due to the weight of the anchor is 1,500 newtons. The distance from the axis to the point on the lever where the sailor pushes on it is 7 times the radius of the capstan around which the rope is wound. So we have a radius here of r, and then 7r, that's what that was talking about. With what force must the sailor push in order for the capstan to turn at a constant speed, meaning that the net torque is 0. So what do we do?
Add up all our torque forces.
Okay, and then...
We know that T net is going to have to equal 0.
Right, so the net torque is 0. So we're going to say, let's see, we have a tau for this guy. So we can say tau for that tension force. And that's going to be at an angle. So that's going to equal the radius to what?
The one to beta or whatever we like.
What?
Phi. Yeah.
Okay, so we have the radius back to the pivot point, which is sitting right here. Remember, we always go back to the pivot point. Times the tension sine phi.
And we learned that yesterday.
Yeah. Okay, now that is actually going to wind up being, if we use the moment arm,
15.
we can call that big R, the radius, times the tension. Now we also have the tau, the torque of the force being applied by the guy pushing on the arm. So what will that one be?
$7R.
Okay, 7R is the distance away from the pivot point. So we have that. What else? It's not tension this time, but what is it?
Force.
The force, the F up here, is how much he's pushing on it. So 7RF. Now we also have to consider which way he's turning. He's turning clockwise, so this is negative 7RF. Good. Okay, now the sum of the torques. So we're going to add these two things together. We know that the 7RF is negative.
So RT sine phi is equal
or just RT.
Oh yeah, is equal to.
Now, which way is this torque here with the anchor? Which way is this one going? Clockwise or counterclockwise?
Counterclockwise.
It is counterclockwise. If you think about it, if the guy lets go of the bar, which way will the thing spin? Counterclockwise, right? The anchor will pull the bar, the anchor will drop to the bottom of the sea, and the bar will spin around counterclockwise. Make sense? Okay, so this RT is positive. So I have RT minus 7RF.
Equals 0.
The sum of the torques is 0. That's right. So this is going to equal 0. Okay? Now, I want to solve for what?
R. Wait, no, you want to solve for the force.
Right. The point of the question was, with what force must the sailor push? Okay? So we want to solve for F. So what I'm going to do is I'm going to move this term over here so that it's positive. So RT equals 7RF.
You can divide by R.
I can divide out the R completely.
And then
Divide by 7. So I have T over 7 equals F.
So 1500 over 7.
Yep, 1500 over 7. That is 1500 what, by the way? Newtons over 7 equals F. So what do we get?
214.3.
214.3. So with significant figures, this will be what?
210.
210 newtons. There we go.
So now,
Is there like a meter I could use to measure how many?
So the reason that we were able to use the moment arm here is because this anchor, probably on the boat, this force is always going to be applied in this direction. And as we wind this around the little spool or whatever it looks like here, the little whatever this is as it comes in will always be perpendicular right here, which means that this radius will always be forming a right angle right there, which means as I draw this line right here, that will always be the moment arm, okay? And the tension will always be directed along that cable or rope or chain or whatever, which means I can always use this formula right here.
So phi equals 90.
Yeah, so since we always have that 90-degree angle right there, we're directed along the line of action. I can use the moment arm rather than the angle, so that's why I was able to switch over to RT. Okay? Good question.
Oh, we have this one.
Oh, you don't have this one? Okay. So look in the next section. Did it pop up on the start of the next section?
no.
Oh, all right. Well, bonus problem. 2 forces act on the wheel shown. What third force acting at point P will make the net torque on the wheel 0? So we need some sort of force applied to point P that will make the net torque 0.
So what is that? The one pointed directly away from the pivot point. What is that?
I don't know. Some extra force.
That equals 0? Oh, because it's not doing anything. So since that is that and that is that, I'm going to say what I think.
You got a thought?
Yep.
You got a thought?
No.
You? What do you guys think?
A.
A?
I said D.
D?
I was going to go C or D.
C or D?
So the reason I think it's not C is because since it's, there's less of a radius there, I think it's got to have a greater force acting on the
Okay.
negative direction to counteract the positive force. So the arrow pointing directly away from the pivot, that's like there's nothing there. There's no torque there.
All right, good. So let's talk about that real quick. Because the force is immediately on the pivot right here, there is no radial distance So therefore, we don't even need to consider this one. It's not a part of a torque. Okay, so only thing we got to consider is the one at the bottom, which is turning the wheel which way?
Clockwise.
Positive direction, clockwise, counterclockwise, right?
Okay.
So we need something that is going to turn the wheel clockwise to
Negative.
counter it, okay? So does D turn the wheel?
No.
It does not turn the wheel at all, actually. So it's not D. Does E turn the wheel clockwise? So it's not E. Does C turn the wheel clockwise?
Yeah.
Okay, so we'll leave that alone. Does B turn the wheel clockwise?
Yeah.
Actually, no, it does not, right? So does A turn the wheel clockwise?
Yes.
All right, so it's either A or C. Now, logically, with the point P being inside the edge of the wheel, the radius is less. So in order to counter the radius being way farther away than the point P, what must be true about the torque?
Double if it's hot, you have lot more.
You're going to need to increase the force in order to counter the torque that the farthest point is generating, right? So we're going to need C or A. We're going to need probably A. Yeah. That's how you come up with that one. Okay? Remember, the direction matters, also the radius matters, also the force matters in rotation. Okay? All right, good. That's it.